Okay. All right, they started work on the roof this morning. I spoke to the chap in charge and asked him not to work on the roof during 2 to 3. So keep fingers crossed we don't suddenly get bang, crash, wallop. Hopefully he won't do anything for the next hour. So let's see how we can do. All right. So so we're looking at the integration of the nervous system and the muscular system, and we were just going to have a quick look at reflexes. Knee tap reflex is pretty simple. It's called a myotatic reflex. So some of you may have had this done at the doctor or by the athletic trainer. If we tap the patella tendon, then that tap puts a stretch on the quadricep, and then if we stretch the quadricep, remember we're going to stretch the muscle spindle. So then we see a message sent through the sensory nerve of the muscle spindle to the spinal cord, and that sensory nerve synapses with the motor neuron back to the quadricep and stimulates the quadricep to contract. And so we see that reflex kick action happen. Okay? What also happens is that sensory neuron from the muscle spindle synapses with an interneuron, and the interneuron synapses with the motor neuron to the hamstring. So that stimulates the hamstring. It's called an inhibitory interneuron because it stimulates the hamstring to not contract. Right? Because obviously if I had contraction in the quad and the hamstring at the same time, I wouldn't see the knee jerk reflex. All right? So we have the sensory nerve synapses with the motor nerve for the agonist muscle, and we see contraction, and it synapses with an inhibitory interneuron, and that stops contraction in the antagonist muscle in the hamstring. For the students, for the AT, PT, OT people, if you're interested in how they grade that knee jerk reflex, there's a box on page 120 that gives you the grading rubric for a knee tap reflex there. So what we see happen with training then, if you think about when you first start to learn a skill's very gross, right? I have to concentrate very hard, I have to think about what I'm doing, I've got to remember where to put my feet, where to put my hands. So there's a lot of cognitive input into the motor skill when we first learn it. As we get better and better at it, there's less and less cognitive input, and if it's a skill that involves reflexes, what we see is more and stronger reflex action, more coordination, more timing involved, and some of that is going to occur at the reflex, at the spinal level. So when we're training, what we do is we actually end up supporting and improving these reflex responses. So particularly for skills like close quarter catching or striking in cricket or baseball. These skills are physiologically impossible to do voluntarily, right? That ball moves so fast from the pitcher that if I wanted to voluntarily control and change my shot, I can't do that. There isn't enough time from the ball leaving the pitcher to the ball reaching me for me to send a signal to my motor cortex to make a decision, and the motor cortex to send a signal back to the muscle to contract and hit the ball, right? So when I'm good at these skills, that's occurring very much at the reflex level, okay? So what we see is what we call reciprocal innovation, all right? So again, here's my afferent fiber, my sensory fiber from the motor spindle, going to the spinal column, synapses with the alpha motor neuron, which comes back to, in this instance, the quadricep, right? This is the agonist muscle, might be a bicep, right? And it synapses with an inhibitory interneuron to stop the antagonist muscle from contracting, right? It can't tell the antagonist muscle to relax, because we don't have that ability, but it stops it from also contracting. If we didn't have the inhibitory interneuron and the afferent sensory neuron synapsed with both motor neurons, we'd see contraction in the agonist and the antagonist at the same time, and then the motor skill couldn't happen. Right? If I want to contract on one side, unless I'm looking to hold stationary, I need the other side to relax. Right? Does that make sense? So we see this pathway improves with training. So there's a training effect on the nervous system here. All right, so we were talking, we said that the main separation in the nervous system is the central nervous system and the peripheral nervous system. So let's have a very quick look at the peripheral nervous system. This is everything outside of the spinal column, right? And it's responsible for transmitting messages, information from the sensory nervous system to other tissues and organs, all right? Everything else outside. It's also split in two. So we have the autonomic nervous system and the somatic or sensory nervous system. The autonomic nervous system is in control of functions that are unconscious, right? Things that I'm not aware of, that I'm not consciously thinking about and controlling. So your heart rate, your blood pressure, your digestion, your breathing, although as we will see later, breathing is an interesting one because it's one I can consciously control if I want to, for a period of time until the autonomic nervous system kicks back in, right? In Eastern philosophies and practices, they believe that you can also control your heart rate to some degree, right? So they will say, okay, if I meditate for long enough, if I do it for years and years and years, if I concentrate, if I focus, if I train it, I can lower my heart rate by choice, right? The Western hemisphere wouldn't necessarily agree with that perspective, okay? But it's quite an interesting dichotomy there. So the autonomic is divided into sympathetic and parasympathetic. Okay, so remember this is controlling unconscious functions. my sympathetic nervous system is my fight or flight. All right, I have to get ready to either fight to save my life or run to save my life. Okay, so that means it's stimulating, it's going to increase heart rate, it's going to increase breathing rate, right? It's going to stimulate lots of stress hormones to be released so that they can aid glucose metabolism and releasing glucose from the liver, so breaking down glycogen into glucose, dropping it into the bloodstream. Okay. So the sympathetic nervous system is your response to something that's challenging. Okay? That might be something that's dangerous. It might be something that you find thrilling, not dangerous. Someone else might go, "Are you insane for jumping out of a plane?" And you're like, "No, I love jumping out of planes," right? Or cliff diving, or any of those kind of thrill-seeking type activities. But also by excitement. All right, if I'm really excited about something, so when you are going into a competition or you're going to meet a new person or, I don't know, have something really fun, that's also going to stimulate the same system, right? So it's also considered a stressor, as is exercise, right? The parasympathetic, the longer one of the two, is your rest, digest, bring me back down to homeostasis. All right? So can I get back to homeostasis? How quickly? What does that take? Okay? So the parasympathetic nervous system controls bringing your heart rate back down when you've finished exercising or when you've finished having a row with your mum, or increasing blood flow to your skin to release heat, right? It also controls peristalsis, which is the contraction of your digestive system to move food through your digestive system, saliva flow, and bladder function, right? So these last ones then are quite interesting because this is the reasoning behind some of the rules we have around exercise. Like, we don't want to eat a large meal and then go and exercise. Because when I exercise, my sympathetic nervous system kicks in, my parasympathetic nervous system dials down, and digestion dials down. And so that food is just going to be sitting there in your stomach and your digestive system, and that can make you feel uncomfortable, depending on what, obviously, the exercise is. I mean, if you're going for a stroll with the dog after dinner, that's not going to be so dramatic. But if you're going to try and compete, then you don't want that heavy feeling in your gut, right? Saliva flow. So you might find when you exercise that your mouth gets dry much faster than it does when you're at rest, right? Again, because sympathetic nervous system is predominant and parasympathetic is being dialed down, right? And over time, if you go for a long walk or a long bike ride, you might find that, oh, I don't need to go for a pee, right? I drank all that water, but I don't feel like I need to go for a pee because we dialed down bladder function. So, autonomic nervous system, okay, and then sensory nervous system. So we've got the ANS and the SNS, okay. The sensory nervous system is responsible for relaying information from the external environment to the central nervous system. So that includes Golgi tendon organs and muscle spindles, all right, because they're outside the central nervous system. But also outside you. So your vision, your hearing, your touch, right? So the sensory division is going to relay that information from sensory organs, whether they're in your eyes, your ears, your skin, your joints, to the central nervous system, and then the motor division is responsible for bringing the command back from the central nervous system to the muscles. Okay, so when we're exercising them and competing, or even if we're just exercising for fun, to stay healthy, to stay fit, then we are interested in the idea of fatigue. And what does fatigue represent physiologically? Right? So there's a lot of work to be done to understand fatigue properly. But we want to split it physiologically into two areas, because we see peripheral fatigue is very different to central fatigue. All right? So we've got our peripheral fatigue. We're looking at what's going on in the muscle tissue, right? Why am I seeing fatigue? Why am I seeing a decrease in force production? Bless you, okay? Fatigue equals a decrease in force production, physiologically, all right? So that can happen. We've got many different areas within our muscle contraction that can get affected by fatigue. It could happen at the interaction between the T-tubule and the sarcolemma, right? Maybe, for some reason, right, we haven't done action potential movement yet, that comes Monday, but, Monday? No, yes, must be Monday. It could be that this signal transfer down the T-tubule slows down, right? Perhaps there's not enough potassium or enough sodium, okay? Or enough ATP, even, because to move potassium and sodium backwards and forwards across the membrane takes ATP, okay? So we could have fatigue occurring here. It could occur due to there not being enough calcium available left in the sarcoplasmic reticulum. So if I've been working for a long time and the calcium is flooding out of the sarcoplasmic reticulum into the muscle tissue, and I'm not moving it back into the sarcoplasmic reticulum quickly enough for some reason, that could be a site of fatigue. Okay? We could see fatigue at the cross-bridge formation. Again, particularly if ATP availability is low. Right? Or if we're working anaerobically, if my pH is changing. Right? If that pH is changing and affecting the glycolytic enzymes, then that would slow down ATP production and reduce how much ATP was available. Right? So this bottom part of the diagram here relates to what we covered talking in chapter 4, right? And where fatigue might occur there. When we look at central fatigue, it's a little more complicated and we don't know quite so much about it. So we know that psychologically, how I feel or how determined I am or how motivated I am impacts force production, right? So if I'm hugely motivated to do something, then we see higher force production than if I'm kind of, I don't really care, right? So that idea that someone's willpower to achieve something plays a role is very true. Now, remember though that we said that willpower alone, right? I can't will myself to win 100 meters if my legs are full of slow twitch fibers, right? This isn't enough, okay? But given that I have the physiology to do the job, then my willpower, my psyche, my motivation to do something can play a role in how quick, how powerful, how much force I can produce. Which is why, which is one of the reasons why we see personal bests at World Championships and Olympic Games and European Championships, right? How many people in any sport get their PB in their weekend training session? Anyone? I mean, I've never heard of it, right? Because you might work really hard at your weekend training session and you might be fully focused, but it's different when you're out there and it's World Championships and everyone's screaming and you've been training for this all your life, and right? There's an extra bit coming here, right? Does that make sense? So there could be fatigue then because I'm bored, I'm not motivated, I'm tired, right? Tired being different from fatigue, right? I'm mentally tired, I'm burnt out, I'm actually tired because I didn't sleep well, right? I'm hungry, I don't want to be here, right? There's all kinds of variables that could feed into this box here. Okay. Then we have our motor output. So the motor output, the signal that is generated in the motor cortex, could be somewhat dictated from here, right? Or there could be another form of fatigue going on with the initiation of that signal, right? If there's a chemical imbalance, or if you've been going for a long time and the chemicals are running low, right? If my neurotransmitters are running down. And the same here with the motor neuron. What if the myelination is starting to degenerate, right? So as I get older, we see quicker fatigue within the motor neuron, because just as a result of aging, we see degeneration and myelination on the motor nerves, right? That's one of the reasons why we slow down a bit physically as we get older, right? Even if I train really hard and I stay active and I'm all bouncy and whatever, I'm still slower than I was 20 years ago, right? And there's nothing I can do about that. That's just aging, okay? This is also, interestingly, where we see the problem for multiple sclerosis, right? It's not a fatigue issue per se, but multiple sclerosis is a degeneration of myelination, and so the signal, if you've ever seen anyone who has multiple sclerosis, it's not that they can't move, but their moving is very uncoordinated and kind of out of time with itself. And it takes a long time for them to make that movement occur because their motor nerves don't have a correct level of myelination, and so it takes a much longer time for the signal from their motor cortex to reach the muscle than it does for any of you.
So where would like Parkinson's come from? Is that in the motor output or in the neural?
I'm not sure about Parkinson's. I don't know very much about that one. Because Parkinson's is the one with the shaking, right? Yeah, I am not sure what causes that one. It's got to be in here though, somewhere. But I don't know if it's at the motor cortex level or if it's at the motor nerve. Right? So we've got a lot to learn about this, obviously. A lot to learn. We know quite a bit about fatigue down in the muscle tissue because it's easy to get at, it's easy to test. Okay? Okay. So, motor units. I'm going to go quite slowly because this is typically an area of confusion, I have noticed, right? So if I'm going too slow, please throw something at me. If you need me to go even slower, throw something at me. Make it different colors, maybe. Let me know. Too fast, too slow. Right? A motor unit. Okay? A motor unit is a motor nerve and all the muscle fibers that connect to that nerve. Right? So, that's a motor unit. Right? That's a motor unit. Right? One motor unit is a motor nerve and all the muscle fibers that that nerve synapses with. And that can be hundreds. Right? We draw it very simply like it's only 3 or 4 per nerve, but it can be hundreds. Okay? So the motor unit isn't just the nerve, it's the nerve plus the fibers the nerve synapses with. Okay. So it's a functional component of muscular activity. This is where the signal reaches the muscle so that we can see contraction. So alpha motor neurons, fancy term for a motor nerve, have relatively short dendrites that receive information within the spinal column. We have our cell body, and then they have one axon that carries that impulse, that signal from the central nervous system out to whichever muscle they're synapsing with. Okay. Now I said last week maybe that the ratio of type 1 and type 2 muscle fibers that we have is genetically determined, and it's pretty set. Well, it's mostly set before we're born, but during the first year of life there's a little bit of adjustment going on. By the time you're 1 year old, your ratio is similar to what you will have as an adult. Okay? So that genetic determination doesn't actually occur at the muscle fiber. It occurs at the nerve. Okay, so it depends what kind of motor nerve is attaching to the fiber, dictates what kind of fiber is generated and produced. okay? So these motor nerves then, or our motor units, because the nerve is dictating the whole unit, we have three options, okay? They can be S, slow, and the muscle fiber that will develop will be a type 1. Okay? They have a relatively small cell body compared to the other types. Then we have FFR. And FFR is a fast fatigue resistant. So it's faster than this, but it's somewhat fatigue resistant. Because it's able to use some oxygen to make ATP, right? It's not great at it like number 1, but it can use some oxygen. Okay? Then we have FF, which is fast fatigable. Is that how you spell fatigable? That's weird. This one has a larger cell body than the S, and this one has the largest in comparison. Right? Now this one can behave more like a type 2A with training. So in the lecture that you watched on video, we talked about training adaptations and the fact that we don't see any type 2 fibers turn into type 1 fibers, and we don't see type 1 fibers turn into type 2 fibers, but within type 2, we can see some adjustment, depending on the training that we're doing. So does that make sense? Okay. So that means then when we come back to this diagram, all right, that if this motor nerve is S, then this is a type 1, this is a type 1, and this is a type 1.
Are you calling it S just because it's small, or what is the S in?
Slow.
Slow.
But I think it helps that it's also S for small, because that helps you remember that they have the smallest cell body. Right? If this is FFR, then this is a 2A, this is a 2A, this is a 2A, and this is a 2A. Remember back to that slide, that cross-sectional slide, right? That one muscle is not type 1 or type 2. a muscle fiber is type 1 or type 2, and a muscle can be made up of type 1, type 2A, and type 2X. Right? So this can all be one muscle, right? Because one muscle has way more than one nerve. When we draw it, when we look at diagrams, we simplify it and show it like there's only one motor nerve coming into the muscle, but there's loads, depending upon the job the muscle has to do. Right, so this motor unit is slow, and it synapses with type 1 muscle fibers. Okay. This motor unit is fast fatigue resistance, and the muscle fibers involved in the motor unit are type 2As. If it was an FR, right, if I make this FR, then this is a 2X, this is a 2X, and this is a 2X. And any others that it attaches to are 2X. Right? Motor unit can't be two types. A motor unit is one type, period. I have lots of different motor units within one muscle. And the ratio of the motor units then dictates what I can and can't do as an athlete, what I'm good and not good at. Does that make sense? I think if you combine this diagram with the slide that shows you the different shading of different fiber types within one muscle, that you'll get the connection. So if we understand this, then we can start to understand the idea that depending on the job the muscle has, right, how much control is required from that muscle, okay? If I need really good control, right? So we as adults, most of us, unless we're dyslexic or we have bad eyesight, but if we're typical adults, we take reading for granted, right? Is reading a motor skill? Technically, reading is a motor skill because in order to read, in order to scan across a page, I have to move my eyes. And to move my eyes, I have to contract muscles. So technically, reading is a motor skill, right? It's a fine motor skill, like doing up a button on my shirt, right? It's not going to keep me healthy, well, keep me mentally healthy, but it won't help my cardiovascular fitness or anything. But, right, I have to contract muscles to move my eyes. So, in my eye, the motor unit, so let's just forget what type of motor unit it is, but in my eye, a motor unit may only have between 5 to 10 muscle fibers. Right? So I've got 1, 2, 3, 4 plus 1 to 6 more fibers. Because to control that movement, that very fine movement, right, that needs a lot of control. So I don't attach to piles, and I don't want to generate piles of force at one time, because my eyeball might shoot out the side of my face. That would probably be very good, right? Could do. You can pull your eyeballs out, actually. They're not really attached very much. They're kind of independent things in there, right? Now, if instead of looking at the eye, which needs fine motor control, we look at a calf muscle, right, that needs gross motor control, when we need to be able to generate power to walk, to run, to jump, right? In a calf muscle, a motor unit could have 1,000 muscle fibers within one motor unit. Because we want to send the same signal to a lot of fibers to all contract at the same time to generate power and movement. On average, if we look across, and this always seems like an odd statement to me, but you will see it in several different textbooks. On average, a motor unit is about 100 muscle fibers, contains about 100 muscle fibers. I'm not sure how useful that piece of information is, to be quite frank, because nothing is average, right? It seems like an odd, it's like on average, women are 5'4". What does that mean? You know, who is exactly 5'4" in this room? Not me. Right? So, I mean, it's kind of a useless piece of information in some ways. Right? So does that make some sense? It also explains how we control things very tightly versus how we generate lots of contraction at the same time in other types of muscles. In my fingers when I'm typing, I don't need to hit the keyboard really hard. Okay? So I don't need lots of muscle fibers contracting at the same time. Good? Okay. I would recommend that you take a little time to review that before Monday, because on Monday we'll start looking at action potentials. So that's a lot of chemistry coming up on Monday. All right, so I would like to, if anybody's got questions about motor units and nerve types and things, I'd like to clear that up first before we jump into heavy chemistry stuff. Okay? It is supposed to be quite warm this weekend, although crazy windy on Sunday. So enjoy, get outside, get some fresh air, because it's been a bit cold to spend time outside this week.
Yes.